Welcome back everyone. In this episode we will see how to generate the VHDL description of our hardware accelerator for spiking neural networks, starting from the software description we created in the previous tutorial. So let's first of all open the Python script. We need to include the component of Spiker Plus which is in charge of generating the VHDL code, which is VHDL Generator. When putting the accelerator on the FPGA, we will work with a fixed point representation. So we need first of all to specify the amount of bits to dedicate to each of the internal parameters of the network. We can do this through a Python dictionary, again, in order to make the configuration human readable. In particular, we can specify the amount of bits to dedicate to the synaptic weights with the weights bitwidth parameter. And for the moment we will start with large values in order to guarantee that the network works properly. In the next tutorials we will see how to automatically configure and pick the best values for these parameters. The second parameter we can specify is the number of bits to dedicate to the neuron, so to the membrane potential of the neuron. Finally, working with a fixed point representation, we need to specify the number of decimal bits to use in the representation. So in particular, where the point in the fixed point representation will be placed. To instantiate and run the generation of the VHDL code, the process is similar to what we saw in the previous tutorial with the net builder. So first of all, we instantiate the generator. Specifying the software object that we want to translate into VHDL and the configuration of the bitwidths. In a second step, we can then generate the VHDL description of the network. Let's describe again these two steps with two simple comments. In order to see the output of the VHDL generator, let's start to print the VHDL code that will be generated. And then, running the Python script, we can see the VHDL description of the spiking neural network. Again, the net builder will print information about how the network was configured. Again, we will see the software object generated by the net builder. And then the VHDL generator will log to the screen, will print to the screen the VHDL code describing the network. You see that there are two generic values which can be configured. And then we see all the input and output signals of the accelerator, so the clock, the reset, start, and all the signals that allows to communicate with the accelerator, so with the sample ready, and so on. Here all the components which compose the network are instantiated, like the first layer of 128 neurons and 40 inputs. 40 is the default value. The second layer with 10 neurons and 128 inputs. All the signals connecting the components are declared. And then we can instantiate and connect the components within the network. If we want to compile and put our component on the FPGA, we need to store the generated VHDL on file. Spiker Plus provides also functionalities to automatically write the code on a file. let's call the corresponding functionality to write the VHDL. And in particular, we need to provide the VHDL object that we just created with VHDL Generator. Let's execute it again. Now you can see that an output directory was generated. The default name for the output directory is output, and if we look inside this directory, you see all the components that are part of the Spiker accelerator. So starting from basic components like address converter, address subtractor, and so on, and going through all the layers and the control parts. You see two components for the two different types of neurons are generated, one for the neuron with the subtractive reset and the other one for the output neurons which have a non-reset, so will be not resetted. And then all the ROM that contains the synaptic weights of the network. Once we generated the files containing the VHDL description of the accelerator, Spiker Plus allows also to automatically compile these files. So let's include the compile VHDL function from spikerplus.vhdl. So compiling all the components that you saw before in the output directory is as simple as running a single Python line saying compile VHDL and specifying the object containing the VHDL description of the network. If we now run the script, you will see messages from the Vivado software, that is what is running under the hood to compile the VHDL code, saying printing information about the compilation steps. When developing these large projects, generally you organize the code into multiple files, and as you saw in the output directory, Spiker Plus does the same. And then, after compiling all the single components to check that the VHDL code was correct, the subsequent step is to consist into elaborating the architecture, so to connect these components and to see if the connections are properly done. We can do this with the elaborate VHDL and again passing the VHDL object generated by the VHDL generator. Again, when running the script, you will see prints from Vivado about both the compilation step and the elaboration step. And you see that everything is okay. So no errors during the elaboration, so all the components are properly interconnected one to the other. Up to now, we generated our code in the default directory that we saw is named output by default. Spiker Plus allows to specify a custom name, so you can also generate different versions of the accelerator into different directories. So let's select Spiker as a target name for the directory. The important thing is that all the functions interacting with VHDL code must use the same directory, so write VHDL, compile and elaborate must work in the Spiker directory. As you can now see, a new directory was created with the name we selected, so Spiker, and again this contains all the files describing the architecture. In this first run, we didn't specify any parameter to the generate function, and the default of the generate function is to generate a functional architecture, so something that is not directly synthesizable. You see in particular that the ROM components comes in couple. In particular, a ROM specifying the size of the layer and a file with the same name plus an IP attached to it. If we look inside the first component, the one without the IP at the end, we see that this is a simple ROM containing a number of outputs equal to the number of weights that we expect to read. In particular, being this the 10 neurons layer, we will see 10 outputs. And then what this component will do is simply instantiating the second component, so the one with the IP at the end. you can see that this is a ROM with a single large output, in this case of 80 bits, containing all the weights in a single word. What this component will do will be simply to map different portions of this large single word to one of the output of the ROM that will be connected to the neurons. Now, if we look inside the IP components, as I said before, the description that Spiker Plus generates by default is a functional description. So this ROM will contain hard-coded all the weights of all the neurons as long words of 80 bits in this case. The problem with this kind of description is that if the network is too big, the weights cannot fit within the lookup tables of the FPGA. So if we want to specify to the VHDL generator to generate something that can be synthesizable, we can do it through the functional parameter. By default, we said that functional is set to true. If we want to generate something that can fit within the FPGA, we can set functional equal to false. Now, when generating the code, we can specify a parameter to write VHDL, that is rm, and if we set this to true, the previous directory will be removed before generating the accelerator again. This guarantees that all the old files are removed and we can generate the new files in a directory with the same name. If we now run the script, in the elaborate phase, you will see warnings regarding the ROM IPs. So we generated the accelerator in a different ways, and the elaboration will report these ROM IPs as not existing, so it cannot find this component. And this is because we will include them as separated blocks in the Vivado tools. I will show you the steps more in detail in the next tutorials. If we look at the files generated within the Spiker directory, now we have a different couple of files. We do not have the IP anymore, and in fact the elaboration doesn't find it, but we have a COE file. Now the component without the IP attached at the end is the same as before, but this is instantiating the IP component. If we look inside this COE file, it is a file in a standard format that is used by tools like Vivado, well, like the ones that automatically generate ROM component or similar, and this simply contains, in a standard format, all the weights similarly to before. There is another issue. In particular, you can see that the network, that the accelerator expects to receive the input spikes as a set of bits all in parallel, and returns the spikes as a set of output bits again in parallel. The problem is that if the amount of input spikes is too large, we risk to not be able to fit within commercial boards that contains a limited amount of pins. In order to guarantee that the accelerator fits such commercial boards, we can specify the interface parameter and setting it to true in order to ask Spiker Plus to wrap the accelerator within an interface that limits the number of pins in order to connect them to physical pins on the board. If we now run the script, you see that the top entity is now called full accelerator. You can see that the top entity is full accelerator. And if we look inside the full accelerator, you see that there is a single bit signal corresponding to the input spike associated with an input spike address, which allows to select the corresponding input spike, providing them one by one. In the same way, we can output the output spike one by one. This wraps the network component, and this simply includes a decoder in input to provide the spikes one by one, and a multiplexer in output to select the output spikes one by one.